All right, so let's look at dimensional analysis one more time. In this case, we're looking at this, we're going from grams to grams. So in this case, we see that anytime we see grams, we're going to need our molar mass, and we see that there's the molar mass, and there's our molar mass. So we have our nitroglycerin molar mass and our CO2 molar mass. That's what we have. Remember, we always have to use our mole ratio, okay, to convert from nitroglycerin to CO2. So we're going from grams to grams. Okay, rules still same apply, the same that it applies, that you need to have, anytime you see grams, you need the molar mass, and that's why we have the molar mass twice, because we're going from grams to grams. So let's look at an example problem and try to tackle this. It says cholesterol, which is C27H46O, can be metabolized into carbon dioxide and water in a process very similar to combustion. What is the volume of water produced by the metabolizing 5 grams of cholesterol if the density of water is 1 gram per milliliter? So looking at this is, what is the volume? Now it gave us the density, which we can figure that out. If 1 gram per milliliter, basically with water, what that means is that 1 gram is going to equal 1 milliliter. So we find the number of grams, we find our milliliters. So it's really only going from grams of cholesterol to grams of water. Okay, so anyway, we need a nicely balanced chemical equation. So it's a lot like combustion. So we'll start with our C27H46 and O. Now combustion, remember, it's just with oxygen gas, produces our CO2 plus our H2O. So let's go ahead from here and let's balance it on out. Okay, so we have our 27 carbon. We need 27 carbon, so we put a 27 right here in front of the CO2. We have 46 hydrogen. Okay, and we have water over here. It has a 2 right there. So 46 divided by 2 is going to give me right around 23. Okay, so we're looking at our oxygen, and what we see is that we have 3 oxygen. And over here, we have our 27 times 2 right here. That's going to give us 54, and then we have 23 oxygen, so 54 plus 23 is 77, which on our reactant side, we already have 1, so we just need 76 more. So what times 2 is 76? Well, that would be 38. So there's our nice and neat balanced chemical equation. Okay, so when we're looking at this, we just want to look at what we're dealing with. Okay, so we're starting with cholesterol, and we're trying to figure out grams of water. So the first thing that we always write down, that we're always going to use, always need, is our mole ratio. So let's go ahead and let's write that down. And we write that down, it's a 1 to 23 ratio. So 1 mole of our cholesterol, that's C27H46O, equals 23 moles of H2O. Now, since we're starting with grams and we're going to grams, we're going to need the molar mass of both of these guys. So we find the molar mass of both. Water, you should have memorized. 1 mole of water is right around 18.02, so we'll just say 18 grams of water. We use water a lot, that's one you might want to memorize. And then all we have to do for our cholesterol, 1 mole of our C27, so 27 carbons, 46 hydrogens, and an oxygen. That'll give us a molar mass right around 387 grams. Okay. And now that we have kind of our conversion factors set up, from here we just go ahead and we work out the problem. So we're starting with our 5 grams of cholesterol. So 5 grams of our C27H46O. Set it up. We'll probably use that much space. And we see we're starting with grams, so we got to go from grams to moles. Well, we use molar mass for that. So we'll go ahead and put I don't want to take all of that. Go ahead and put that guy on the bottom. There's our conversion factor. Okay, that on the bottom. Put the other half of it on the top. We can see it there a little better in black. And then we keep going. We see that this unit will cancel, and now we need our mole ratio. So to convert from moles of our cholesterol to moles of water. So we take this guy right here, goes on the bottom, and the other part of the conversion factor, it equals, goes on the top. And then we keep going because we need grams of H2O. So match it up. We have to multiply. Oh, forgot our 1. Make it in black so we can see it. And then all we have to do is multiply the top. So 5 times 23 times 18, all divided by our 387. And we should get an answer right around 5.35 grams of H2O. All right, let's move on to our next problem. It says that uranium hexafluoride reacts with pure sodium in a single replacement reaction. How many grams of pure uranium can be extracted from 2 kilograms of uranium hexafluoride? So a little bit of trick here. We see that we're starting with 2 kilograms, which we need to go ahead and convert that into grams. So that would just be our 2,000 grams of uranium hexafluoride. So we would have that. Okay. And when we're looking at this, if we have 2,000 grams, we're going to convert into how many grams of pure uranium. So when we're doing this, need a nice balanced chemical equation. So it's uranium hexafluoride. So when we're looking at this, uranium hexafluoride, so it's uranium, and then hexa is going to mean 6, so 6 fluorines, plus it's reacting with pure sodium to produce our it produces our pure uranium, so just uranium by itself, and it's a single replacement. So now sodium is now bonded to fluorine, so we have to crisscross there, which in A and F they're both plus and minus, so we crisscross the ones and it's just NaF. Okay, so from here we just go ahead and balance the chemical equation. So we need 6. We have our sodiums are balanced, uraniums are balanced, the fluorine's the only thing it's not. We have 6, we need 6, so we put a 6 right there. Okay, it changes our sodium, so we got to come back here and put a 6 right there. And now we have a nice, neat, balanced chemical equation. Now, in looking at the problem, it's saying that we're starting with 2,000 grams of uranium hexafluoride. So we're starting here, and it wants to figure out how many grams of uranium. So the mole ratio that we're going to have is just a 1-to-1 ratio. So 1 mole of uranium hexafluoride equals 1 mole of uranium. Okay, now since we're starting with grams and we're going 2 grams, we need the molar mass of each. So when we're dealing with this, we look at our molar mass of uranium hexafluoride. So 1 mole of uranium hexafluoride equals right around 352 grams of uranium hexafluoride. Okay, and then 1 mole of uranium equals right around 238 grams of uranium. Okay, now that we have our conversion factors, we know what we're starting with. We're starting with our 2,000 grams. We just go ahead and fill everything in. So there's our 2,000 grams. Start to fill everything in. So to go from grams of, and this is, or 2,000 grams of uranium hexafluoride. So to go from there to there, we need to go to moles. So that guy will go on the bottom. The other part will go on the top. Then we keep going, and we put our mole ratio, which there's a 1:1 ratio. And then we keep going, and then we put, to go to grams, we put moles on the bottom. Make it where you can see that. 1 mole of uranium equals the grams of uranium on top. And then all we do is multiply 2,000 times 1 times 238, all divided by our 352, which should give us an answer that's right around 1,352.3 grams of pure uranium.